Hi, so what I wanted to do before I started the next section of notes is I wanted to show you a couple of resources that I put into the OneNote notebook for you. This is a GeoGebra applet that's going to give you an opportunity to basically visualize what's going on with the um, kind of the left sum, right sum, and the midpoint sums. So here's an example. It's like clearly kind of taking a look, see how our function is increasing from 0 up until we get to 10. Our interval is 0 to 10. This is the x squared example that we were working on. And you can see that I'm at a left Riemann sum right now. And that left Riemann sum is clearly an underestimate. Now up here, I can drag this where it says center, and that's going to change the selection of what point I'm using for the sum. So I'm going to slide it all the way over to the right. So now you can see that they're using the height from the right endpoint to get it, and you can see clearly we have that overestimate. But kind of the one thing that I did want to show you with this is that, remember I was saying that it doesn't matter what point we're actually picking in the interval, that as you kind of let this go across, you'll get better and better estimates, and then it starts getting worse. So you're under, and then getting closer and closer and closer. At some point, you'll have a fairly good estimate, and then as you keep going, then you'll have an overestimate. But the idea here is that it doesn't really matter, because if I start adding more rectangles in, so here we're at 43. So I'm still an overestimate, but kind of as I'm doing this, do you see how the range of the points, they have a very little tiny section that they can move now. So I'm a little under, I'm a little over on that. If I keep adding more and more points, then essentially, does it really matter if I'm on the left or the right? You can't even tell the difference between if I'm on the left and the right. You can see a little bit of the shift going on, but it essentially will turn into the area under the curve very quickly, and you see how it kind of solids up there. So I did want to show you that. I put the link into the OneNote notebook. It's located right here where it says GeoGebra applet rectangular sum. So just click this link up here. You can change the function by typing it in there, and then you can play around with left or right as you're looking at it. So I just thought I would let you know that. Okay, let's go ahead and start our notes, the last notes that we're going to have for this class on these Riemann sums. All right, so here we are with our part 2 of the estimations that we're going to do with our Riemann sums. And with these estimates, we're going to give you another way. Now, prior to this, we were using rectangles to approximate the total distance that's there. So this is that same problem that we've been looking at, this y equals x squared. Now, I did look up for you because I was like, what does the notation that they're using mean? The LRAM, RRAM, and MRAM. And what I learned is that it basically means left Riemann approximation method, right Riemann approximation method, and midpoint Riemann approximation method. But I am going to be honest, I really think that it's a lot shorter just to do L and however many rectangles you want, R, how many rectangles you want, and then midpoint and how many rectangles you want. And that will be fine notation. Also thinks it just saves a little bit of time. All right, so now what we're going to do is we're going to look at the same problem, but let's talk about kind of advantages and disadvantages to using the rectangles. So kind of brainstorm to yourself, what was good about the use of rectangles in order to find these areas? Probably one thing that you're thinking to yourself right now, and it's probably the number one advantage, it's easy to get the area. Area of a rectangle is simply length times width. So length times width, your height times your width is what we were using before. So if we have our height, which is from the function value, times the width, which was our delta x, and that was fairly straightforward in terms of how we were getting the area. Now, some disadvantages to that. All right, so the first thing that's kind of a big disadvantage is that it assumes that on the subinterval that you have a constant velocity, even though that's not true. there is a constant velocity. So even if your curve was curving up, even if you were using, say, the midpoint method, you're assuming that your velocity for this entire time interval from the beginning to the end is the same constant linear velocity coming across here. And that's not necessarily true, and that may or may not be a great estimate. So because of this idea that when you're looking at this subinterval and you're saying it's a constant velocity, what that does is it makes our left and right sums consistently over or underestimate. And so we're not getting a really great estimate of our actual area under the curve with this. Sometimes you say, well, midpoint was better, but it still wasn't, that great by making this assumption that for the entire time interval, we kind of had this constant velocity. So what if instead of me using a rectangle to come across, we decide to use a trapezoid? And we was like, what do you think that would do to our approximation? So if you think about that, is it going to make it better? Is it going to make it worse? Do we think that might be more advantageous to us to use a trapezoid? So let's kind of look at a couple of things on this. Now I'm going to go to the internet right here, where I was using this Riemann sums. And what I'm going to do is, I had it in here, I thought. The ones for the trapezoids, let me find it from, there's rectangular and the trapezoid sums. So here is kind of just a generic idea of taking a look at it. And as you can see, as you kind of envision this trapezoid right here follows along this curve a little bit better than what the rectangle would have done. And in some cases, depending, like even here, depending on how steep or something like you have, you can see that you get a very good estimate. So you can see kind of as I increase this up, we'll get a better and better estimate, because the idea is that if we zoom in far enough and then take a look at what's going on with those trapezoids, you can see that that small tiny section of the curve actually starts to appear linear. Like that was the whole thing about the local linearity, that we could zoom in on that. And so the trapezoids are going to give us a much better estimate more quickly than what we would have had before. Now I also linked that GeoGebra applet in your OneNote notebook down here at the bottom, Riemann sums trapezoid, so you can play around with that. So I would say that kind of our idea of what will this do to our approximation, I think this is going to give us a better approximation, especially if our number of trapezoids n goes to infinity, because that's going to give us much better than we have. So let's go up here and do our 10 trapezoids of equal subintervals, just to kind of see what it looks like. Now, your delta x that we had before is still going to be b minus a over the number that you want, 10. So your width is still going to be 1. Now, the only difference is that, like, when I draw it, I'm going to do it for this one right here in the middle. In between these 2 points, instead of me picking and drawing a rectangle, I'm going to draw my 2 heights and then just connect them with this little trapezoid. Now I went ahead and added all the 10 trapezoids on there. And the idea is that the one thing that you have to remember, which we talked about on a previous video, is if I want to get the area of this trapezoid, I do need to know the area formula that we're looking at. So the area of a trapezoid, remember, is the average of the 2 bases, the parallel sides, times the height. So now in this problem, you have to visualize that the height of one, or actually the base 1, is going to be this vertical line right here. Base 2 is going to be this vertical line, because those are the 2 parallel sides. Your quote-unquote height is going to be going that way for this trapezoid. So your height is actually going to be your delta x that we just calculated. And notice that the height here to get B1, that's simply the function value where you have plugged in the right, oops, sorry, I don't know my left and my right. That would be the function value where you plug in your left endpoint right there. And B2 is going to be your function value where you plug in your right endpoint. Right? And so pretty much kind of running into this, that tells us that our area in this problem is going to be f of, I'll just say left, plus f of the right, divided by 2, because you're going to average them, times delta x. So if we're going to use that to approximate her distance, okay, we're basically going to be able to use these function values and work our way through the problem. All right, so I'm going to write it down. Why don't you try to write it down for number 3 and see what you get, and then we'll compare. So pause for a moment and write it down. All right, coming back in, you can see that kind of taking a look at what I've written down, that you clearly have, it's a little tedious with the left endpoint's height, right endpoint's height, and so on as you go down through here, but it's fairly straightforward, and you just want to make sure you include your 10 rectangles. In terms of the units for this, especially in this problem, remember that the delta x was in hours, okay? Each of these heights is in our kilometers per hour. So even though I average them together, the average of base 1 and base 2 is going to be kilometers per hour times hours, which is going to leave us in kilometers. So it still does the same thing that we had with the rectangles. Now, one thing to do is to go back and look at our left sum when we had 10 was 285 kilometers. Our right sum when we did the 10 rectangles was 385 kilometers. Now take a look at this 335 kilometers that I got using the trapezoid sum. And hopefully you can see, because these are 100 apart and that's 50, that the trapezoid sum is actually, and if you have the left and the right, this is actually easier. The trapezoid sum is nothing more than the average of the left sum and the right sum divided by 2. So this is kind of another little shortcut. You don't always have to write it out using the trapezoid formulas if you already have the left and the right sums. Now I do want you to be careful because sometimes students get confused. Make sure you realize that the trapezoid sum is not going to give you the same thing as the midpoint sum. Because the midpoint, what you did is you averaged the inputs and then plugged them in to get the function value for the height, whereas this is you average the outputs. So even though you're averaging things, you're averaging 2 different things, they are not going to give you the same values. But in terms of which one is a better estimate, I definitely think that the trapezoid or the midpoint is going to be the best estimate that's there. All right, so the important ideas from this is that our net area from A to B can be approximated with a Riemann sum. These are also called Riemann sums, but we're using Riemann sums, which is the sum of trapezoid areas. The second thing is to remember that the delta x, as we're looking at that in this case, delta x is still b minus a over n, but in this case it's going to be the height of the trapezoid. Okay, and then the other one, to get the bases that you have, the f of the left endpoint is going to be base 1. F of the right endpoint is going to be base 2. So when we go to calculate our area is going to equal B1 plus B2 over 2 times your height, which is delta x. And just make sure that as you're doing it, you're using the function value for the left endpoint and the function value for the right endpoint. So this is fairly straightforward. The only other thing that I think I would add down here into this for a third thing, if I can fit it in before I go to the end, is that the shorter way to get the trap sum is to average the left sum and the right sum and divide by 2 if you have already calculated them. Okay, do the homework. and come back.